let's continue to the derivation of the divergence theory. So let's consider an arbitrary volume in an electrical field region and divide the volume into many small ones. So of course, as you can see from the divergence theory, the Gauss's as well as the closed surface integral of the displacement flux. And even though that the equation here is only applicable to a specific point in the space, the divergence theories allow us to expand this relationship to our region, all right? So suppose you have an arbitrary 3D space, and of course it's larger. It can be in any kind of shape. So the field distribution within this region is inhomogeneous, which means that not the same. It can be different at different positions. However, we can first divide this region into many small ones so that the total flux penetrating this region can be expressed as a summation. So here you have, to the left, you have the summation of divergence of t at a point times its neighborhood, a small 3D space. And according to this relationship, the right-hand side of the equation becomes a collection of closed surface integral of this many small region. All right. And the trick is, if you look at this relationship graphically, you know that to the left is the volume integral of the divergence of d in this relatively large region, while to the right is the summation of closed surface integral of many small regions. Note that for this closed surface integral, we are evaluating the displacement flux emanating from this small cubical area. And for one cube and its neighbors, you see they share certain surfaces. So the displacement flux that goes out of this region goes into its neighbors. So the surface integral of the displacement flux at this specific small region cancel out as long as the surface is within the interior of this larger surface. The surface integral cancel out. So you only have the surface integral that is placed at the very surfaces of this larger region. All right. So by knowing that the surface integral cancel out within this larger structure, this result can be written like this: the closed surface integral of vector A can be transformed into the volume integral of the divergence of this vector. So this is referred to as the divergence theory. So closed surface integral can be transformed into divergence operation and volume integral, which can be easier in terms of mathematical operation. 所以在闪度定理里头就是说我们从一个点出发这是一个点的关系式所以那这个的话我们当然可以先前我们昨天已经有讨论过了嘛，对不对？所以某一个点的 散度哈，等于那个点附近的位置小小区域范围里头的那个封闭面积分啊，除上那个面积体积大小，除上这个体积大小啊，那这一个关系可以被推演至一个较大的范围啊，所以在 3.62 里头，我们看到的是一个任意形状、任意大小的区域，而当你把这个任意大小的空间切成很多的小空间，每个小空间哈，这个关系都是成立的。而重点在于，当你切分成小空间的时候，它们相邻面的那个面积分，它的场的方向是固定的，但是面的方向是一正一负，所以会被互相抵消掉。所以这个整体的结果加总之后，整体结果只有在第二步的面积分才必须要来去计算啊，所以前面那一个关系式可以被推演到 3.64 啊，也就是任意向量在任意的空间形状里头哈，它的封闭这一个空间的封闭面积分哈，会等于它散度的体积分啊，散度的体积分啊，所以在数学的操作上相对就比较简单啊。So in example 3.9, we will use Stokes theorem and divergence theorem in succession, so that we can show vector identity. So this thing is referred to as the vector identity. So for any vector A, if you take in the curl operation first, then apply the divergence operation, then it must goes to 0. So this is referred to as vector identity, which is, of course, valid for any vectors. 所以这个叫什么 ？vector identity 叫什么？反正对于任意向量来讲，这个关系式都是成立的那我们这边就在这个 example 里头，就用先用 divergence theorem， 再用 Stokes theorem 来去验证这一个关系So what is the divergence theorem? The closed surface integral of any vector A equals to the volume integral of the divergence of the vector A and Stokes theorem for the closed loop integral of A equals to the surface integral of the curl of the vector. All right. So suppose we have egg-like space, and you divide this region, the surface, the closed surface of this egg into two halves. So you have surface S1, the left one of the shell, eggshell, and S2 is the right one. And now that they share a common edge, which is referred to as C1 and C2 for the two halves of the eggshell. And of course, because S1 and S2 jointly form a closed surface, so the differential surface direction is pointing outward. So you can see that the S1 and the S2 are pointing to the right, to the left, and to the right, respectively. All right. So we first apply our purpose is to demonstrate that for any vector, if you take in the curl operation first, then apply divergence operation, then it must goes to 0. So we want to demonstrate that this thing equals to 0 for in any space. So we take volume integral of this thing. We take the volume integral of this thing, and we apply the Stokes theorem, because according to the divergence theorem, divergence theory, the volume integral can be transformed into the the volume integral of the divergence of the vector can be transformed to the closed surface integral of the vector. So here we identify curve A as this as a vector, say vector B, all right? So you can substitute curve A as vector B into the relationship of divergence theory. Apply it to the divergence theorem first. So the volume integral is transformed to closed surface integral. Okay, so you see you have closed surface formed by S1 and S2, and the vector is identified as curve A. And the next step is to separate the closed surface integral into two surface integrals, which are S1, S2, respectively. And now you can identify the first term and second term are two surface integral, and it happens to have its integrand as curve A, which is the curve of another vector. So then we can apply the Stokes theorem, that is, the closed loop integral of a vector can be expressed as the surface integral of the curve of the vector. So we replace curve A, the surface integral of curve A, as the closed loop integral of A along the specific contour C1. And the second term is recognized as line integral of A along the contour C2. And as you can see in the figure, C1 and C2 are in fact the same contour with different orientation. They are of the opposite direction. So the line integral along this contour C1 cancel the line integral along the contour C2. So it must goes to 0 because they cancel each other. So that we can verify this vector identity, that is, for any vector A, if you take in the curve operation first, then divergence operation later, you always end up with 0. All right? Next, we move on to section 3.4, which we will attempt to derive the uniform plane wave. Okay? Every year, when it comes to this section, I'm getting more and more excited, right? So we finally are going to check or look into the generation of electromagnetic wave, all right? And as I already mentioned, the generation of electromagnetic wave is a process involving both time-varying electrical field and time-varying magnetic field. Based on our observation on Maxwell equation in the differential form, in particular the Faraday's law and Amber's-Kittel law, the Faraday law says time-varying magnetic field will perturb the distribution of electrical field in its neighborhood. So time-varying magnetic field produce spatial variation of electrical field. 时变磁场造成临近空间中电场的变动。所以你看到在 Maxwell equation 里头的法拉第定律，它的左边是电场的空间变动，而右边是磁场的时间变化。同样的，安培电路定律告诉你，磁场的空间变动除了跟电流分布以外，也跟电场的时间变动有关。所以这个叫磁生电，这个叫电生磁。而把两个一起考量，我们就能够 产生电磁波。在maxwell斯韦尔整理出这些 equation 的时候，其实还没有办法用实验来去观察或者是验证电磁波的存在。但是看着这两个式子maxwell 就推论出有一个东西叫做，既然会磁生电，电生磁，就推论出有一个东西叫电磁波。那当然我有提过，他活着，他42岁，好像42还是48岁就挂了哈。所以他活着的时候没有看到电磁波的现象，但是他的学生赫兹就在他过世大概几年吧，就用做实验的方式来验证电磁波的产生。好 ，alright. So the generation of electromagnetic wave, of course, can be happened naturally or manually. All right. Okay. And to simplify our derivation, we will try to simplify the scenario, the operation scenario. So we'll first talk about the generation of the so-called uniform plane wave. So as this part suggests, in this configuration, we have E and H field align on the X direction and Y direction. So E and H field are placed on the XY plane. And Z direction, which is marked with this blue arrow, indicates the direction of wave propagation. So the E and H field which are placed on the XY plane will propagate in the Z direction, or will propagate in either positive Z or negative Z direction. So it's kind of the associated E and H field are one-dimensional problem, a one-dimensional function. So as you can see in these two equations, they are the small parentheses suggest that their only spatial dependence is in the z-axis, and it also has time dependence. So you need to be aware that for propagating electromagnetic waves, it has both description about time and space. 所以对于传播的电磁波来讲，你必须要的一个能够跑起来的电磁波的方程是一个函数，必须要同时拥有时间跟位置的描述。所以像这个 3.66 AB 的这个式子里头，就是一个相对简单的一个起点了。那在这个小括弧里头，你可以看到它们是位置 z 跟时间 t 的函数，好不好？那在这一个设定里头，我们假设电场是指向 x 轴向，磁场是指向 h 轴向，y 轴向，磁场是指向 y 轴向，而电场跟磁场在 xy 平面上面的各个位置都是相同的，只有说你变动 z 的那个位置，你才会看到电场跟磁场的变化，好不好？Right. So, however, we need to note that uniform plane waves do not exist in practice because you need a source. You need an antenna you need an infinitely large antenna so that you can produce a plane wave, an actual plane wave. However, in reality, the antenna size is finite, so the electromagnetic wave generated by a finite size antenna begins as a spherical wave, such as this one. However, as long as it propagates, the radius of the waveform. Now, it starts as a spherical wave. However, as the propagating distance increases, the waveform, the spherical waveform, will approximate as planar surfaces as long as the distance is large enough. So that in practice, the analysis or the assumption of plane wave is still useful and is convenient for our description about the problem. All right. So the analysis for plane wave is very fundamental for propagating problems, as well as transmission line analysis and waveguide analysis, which is related to the microwave circuit. 所以对于空间中传播的电磁波的分析，还有微波电路也就是高频讯号在那个电路板或在导波管里头那个传输行为的这个描述plane wave 应用都还是蛮基础的所以当然我们会先从平面波的推导产生来去做介绍 ，right? Okay, so let's begin with our problem description. So suppose we have infinitely large current source. Or again, in our classroom, assuming that in the middle we have invisible current plane. All right, and the current is going downward. Okay, so you need to imagine that in the middle of the classroom we have in the invisible world of currents, you have uniform current distribution that goes in this direction, and we say this direction is the x direction, all right? So according to the graph, it's going to downward, it's going to the negative x direction. So this is the positive x direction, and if this is the positive y direction, then positive z direction can be found with right-hand square principle, so it goes to this direction, okay? X, y, and z, all right? So in the middle of the classroom, which is marked as z equal to 0, we have an infinitely large plane of currents going down at this very moment. Of course, to generate electromagnetic wave, you need to have a time-varying current source. So the current that goes down at this very moment will change its magnitude and even change its direction. So it will, in fact, to provide electromagnetic wave, the current will goes up and down in succession. All right. So we have current plane that is homogeneous on this xy plane, or z equals to 0 plane. And we can describe the current density on the current plane as Js, which is a vector, because it has direction. And its magnitude can be described as Jst. Now that the function is only a function, the surface current density Js is only a function of time. Why? Because the current stays at this plane. It does not go anywhere, right? So it's just a time function, okay? So Jst is located at the position of z equals to 0. And if you have a so-called sinusoidal current source, then Jst can be returned as Js0 cosine omega t. Okay, so the cosine omega t indicates that this is a sinusoidal function, and what is the frequency? The angular frequency of this function is omega. So the corresponding frequency is 2 pi f is f. Okay, so this is the frequency. As you already know, this is the angular frequency. Okay, what else? So if you observe the currents at z equal to 0, you will find that at t equal to 0, the current goes down and it becomes smaller and smaller and goes up and becomes larger and becomes smaller again and goes downwards afterward. So it's varies as a sinusoidal function, right? As the time progresses, and you can see that the current direction will change every half cycle, right? Every 180 degrees. So the plot shown here is a full cycle, is the current variation, including the direction and magnitude in one full cycle. All right, and the median, okay? The median is supposed to simplify the problem. Suppose the median is free space. So in this classroom, there's no chair, no students, no blah blah blah. Right? So it's just free space. And we apply the two equations, Maxwell equation of Faraday's law in differential form, as well as the Ampere's kilo law. So we use these two equations to derive the so-called plane wave. And the derivation process involves these 4 steps. First is to find applicable differential equation. Second is to find the general solution of applicable equations. Third is find the traveling wave, which is the superposition of 2 traveling waves of opposite direction in general. And the 4th step is to find the so-called specific solution by substitute the initial condition or boundary condition. 所以在平面波的那个推导的过程当中，我们等一下会做这几个步骤，做几个步骤。第一个是选取合适的微分方程式，但这个所谓的微分方程式，也就从我们的那个一般形式的 Maxwell equation 里头找出我们所谓合适是说我们这一个题目它的电场在 x 方向，磁场在 y 方向，所以它所牵涉到的微分方程式相对比较简单比较单纯一点，然后找出它的一般解形式然后再来去找出它的特殊解其实这个大概也就是。然后我们要解所谓的2阶偏微分方程式那只是说这个 suppose 在工程数学里头应该有学过了，2阶偏微分方程式。所谓2阶偏微分方程式，也就是所谓的波动方程式wave equation 好了，那我们就过来看吧So the first step is to find out applicable differential equation, and well, in general, the currents can be of any direction. However, in this problem, we know that the current density J, only flows in positive or negative x direction. So you only have Jx component, you don't have Jy and Jz component, all right? And the condition of you have only Jx currents only leads to this result. In general, to the very left of the equation, we know that the J appears in the Ampere's kilo law. So if you have Jx, Jy, and Jz component, you in fact can write 3 equations. However, you only have Jx component. So the terms pertinent to the Js component is this one. Because this one, well, this is the x component, y component, and z component, right? And for the x component, the current density is in the x direction. This suggests that this component is also in the x direction. So we can find that the time derivative of d is in fact time derivative of dx term in this equation. So we can confirm that this is dx. And to the left is the curl operation of magnetic field intensity. And it's to have the x component, you can have only the hy del hy over del z. Well, to be more general, 事实上那一个式子的等号左边其实应该是这个啦。hz 对 y 的微分减去 hy 对 z 的微分，这两项它的结果都是在 x direction。可是平面波有一个条件，就是像我们刚才讲，我们那个平面波它是什么？电场在 x 方向，磁场在 y 方向，然后嘞，它的那个传播方向在 z 方向嘛。好，那平面波有一个条件，就叫做它的传播方向上面没有电场跟磁场的分量。也就是说，假如你的传播方向是在 z 方向，那你没有 EZ term， 也没有 HZ term， 这个是平面波的一个条件。所以平面波在电磁学里头又称之为 TEM wave。平面波也算是 TEM wave 的一种。TEM wave T 指的是 transverse， 就是垂直了哈 transverse。Transverse electromagnetic wave， electromagnetic， 不写了你应该知道我意思。Transverse electromagnetic wave， 所以这种称之为 TEM wave， 那平面波有 TEM wave 的特性，所以假如你是在 z 方向传播的话，那它就不会有 EZ term， 也不会有 HZ term， 所以呢，你在那个 slide 上面看到的那个式子，这一项就没有了，所以才会变成只有负的 del hy over del z 它这一项经过旋度的操作之后是落在 x 方向的然后你有 Jx 有 dx 的时间微分，然后这是 y 方向的。那事实上，我们刚才讲，对于这个平面波来讲，电场都在 x 方向，磁场都在 y 方向，所以这一项其实不存在。这项也不存在，所以这整项这个式子其实也不用管它，然后最后一项是在 z 方向的那一来你没有 jz term， 你也没有 dz term， 所以这一项也不存在那上面也是通例可以找得出来，所以假如你的电流是 x 方向 jx term 的话，那它所牵涉到的是 x 方向的电场跟y 方向的磁场，所以只有这两项有在这一个情境底下，在这个平面波的情境底下有意义所以 you have y directional, you have magnetic field in the y direction, and you have electrical field in the x direction, which are results of current in the x direction. So down here we have a Jx term which produce hy term according to the Ampere's law. Yeah, Ampere's law, okay? And hy, what is the relationship of hy and by? 还记得吧 ？hy 跟 by 是什么关系？就是乘上一个介词系数而已啊。那第一个跟一呢？乘上一个介电系数的关系啊。suppose 到现在你应该记得，应该可以记起来吧？所以因为有磁通量的关系，所以你看到 by 的时间变化就会造成 ex 项。那 ex 项其实就是 dx 项，所以你会看到这几个式子在这边跳来跳去 ，jx 跑出这一项 这一项跑到这边呢，就产生这一项，这一项就对到这一项，这一项的时间变化又到这一项，好，所以它其实，用中国用语叫什么闭环的哈，形成一个闭环 ，right？ Okay, so for this specific case that you have currents in the x direction, Jx, so it involves only the magnetic field in the y direction and the electrical field in the x direction. And any other equations are not relevant for this case. And to find, the second step is to find the general solution of this problem. And we know that the production of E field from H field and the H field from the E field is in a successive process. So we first try to 好吧，我们先发考卷好了，等一下再来讲这件事。